Hello, everyone. This is Dan McCurry, and today we're going to talk about the intersection of learning, knowledge, and language. Just to give you a quick background about me, I work for a company called Optum. We're part of United Health Group. I'm a distinguished engineer in a group called the Advanced Technology Collaborative, and our role is to help match emerging technology with the business problems within our business units. I'm a solution architect by training, and I've written a couple of books on making sense of NoSQL, as well as the state of healthcare technology with several other authors from Optum. Just to give you some context here, Optum is part of United Health Group, and we have a lot of IT employees, almost 35,000 IT employees, 3,200 data scientists, and we spend a lot of time understanding how to educate people on how to pick the right technologies. Graph technologies is one of the newest technologies, and I think you're going to find that we have to work extra hard at storytelling and other things to help people understand the value of that. Today, we're going to talk a little bit about where innovation is going to be occurring in enterprise knowledge graphs. And one of the quotes I like to use is my friend David Cantor, who has been working on the ML Commons machine learning benchmark projects. And he says, as a technical generalist, he's found that tremendous innovation occurs at the seams of technology. And what does he mean by that? It means where we're not just focused on one domain, such as graph, and not just machine learning, but we're looking at where these domains come together. And that's where innovation is occurring. A lot of the work that I'm doing right now started out with a relatively short blog post I did on Medium in November of 2020, where I started to say, you know, we could look at how to evolve enterprise knowledge graphs by using this thing called systems thinking. And I got a lot of positive feedback from that blog. I was asked to run a half-day workshop for the Knowledge Conference. And I think you'll find that there's a lot of new ideas that might explain how you can use enterprise knowledge graph strategies. So today, I'm not going to talk just about TigerGraph, or I'm just not going to just talk about graphs. I'm really going to talk about how learning, and specifically machine learning, as well as symbolic learning, often called inference, is going to be combining with knowledge graphs, how we store our knowledge about our enterprise, as well as some of the emerging things in large language models. If you've seen GPT-3 or these BERT models, you've seen that there's a huge amount of innovation, that in fact, these large language models are in fact knowledge graphs. And using them effectively is important because in healthcare, at least 80 to 90% of our knowledge is tied up not in tables and columns of relational databases, but it's tied up in documents and clinical notes and in conversations. Every time that we're recording a conversation and transcribing it, we have knowledge in those transcripts, and we can use that knowledge to find insight into the organization. So another thing that we're going to talk about now is this relationship between knowledge graphs and this field of a thinking called systems thinking. And so what we're really saying is we're going to apply a way of looking at the world, a type of analysis, systems thinking, to our challenge of enterprise knowledge graphs, and how to set them up, how to manage them, how to grow them, and how to think strategically about how enterprise knowledge graphs fits into the mission of our companies and how we serve our customers. So just to be clear here, when I talk about enterprise knowledge graphs, just want to be very clear that we think that enterprise knowledge graphs are very different than some of the other definitions out there. When I think of enterprise, I think of things that scale to multiple departments and continue to grow without having to be re-architected. I'm thinking of thousands of concurrent users, hundreds of applications, allowing anybody to do ad hoc queries and making sure that the roles that they have only allow them to see the data that they should see. I'm talking about high availability, things like rolling upgrades, detailed high security, fine-grained control, resource quotas, and a very large library of graph algorithms. And it's something that everything I do, I talk about is it has to scale out. So when I think of scale out, I think of 7 different dimensions. Scaling out our data sizes so we could add more data to our knowledge graph without shutting down the servers. Scale out compute means I can add more compute resources, more nodes to the clusters. I can scale out security. I can allow it to be managed. I can continue to monitor data quality. I can scale out algorithms by adding more algorithms without slowing down the server. And I can square out queries so that I can add more and more concurrent queries as the systems grows. And I just want to be everybody aware that many different organizations out there that are trying to promote potentially their own views and their own products have a different definition of EKGs. So just buyer beware about what do you mean when you think of the word enterprise in knowledge graphs. At Optum, we've been working hard to build an scalable knowledge graphs about healthcare. We have tens of billions of edges in our system, billions of vertices. We're doing millions, tens of millions of updates every day. We have streaming interfaces so that the change reflected in an operational source system will be reflected in our customer service center screens that use the knowledge graph within 60 seconds. We have over 25,000 concurrent users, all of them having 100 millisecond response time to see a full member journey of all of our customers' views. And most importantly, we are now starting to see deep insights about clinical value over all of these systems. What it means is that we can't just look at one dimension of our members. We can't just look at the times they visited our website or the emails or their claims. We have to pull all of these things together in one place, including things like, what is their net promoter score? How does all the different things that we're working on impact their net promoter score? How does their experience with their call centers or how they pick their plans? All of these things are tied together, and we can't look through a straw at one little dimension at a time. Everything has to be together so we can do cross-domain queries. What is our goal? Our goal is to get the right information to the right people at the right time. We're thinking of this as evolving to be what we call the central nervous system of our organization, where we have intelligent triggers and proactive alerts so that all of our consumers in healthcare of information, care coordinators, our physicians, our nurses, every one of our agents, everybody that's working at assisted living centers, all of them can get the right notification of the right information. And it's not just clinical history, it's also through Internet of Things, biometric readings that are happening in real time in our hospitals and clinics. All those things should be able to notify people, and just the right people at the right time should get notifications. Next, I want to define what a system really is. So a system is, in our definition here, a collection of components that interact together to produce some sort of behavior. On the right-hand side, I have a sample EKG system. And you can see that I've broken it down into subcomponents, the source systems that we gather data from, the change data capture events every time there's an insert or update or delete, the streams that we publish those events on, the graph database that we ingest that data into, and all the many UI systems that we build for dashboards and reports and analysis and event noting. And metadata is really a key piece of that. So we can track the lineage of where our data has come from so that any report, we can trace it back to how that system. What's important about this is that these systems are inherently complex. They have lots of subsystems. Those subsystems evolve over time. And what's interesting about this is as systems get larger, and I think getting towards the 10 billion vertex mark is really important, because then we start to see what we call emergent behavior that we couldn't actually predict, but starts to happen as we put together more complex systems. So what is the systems thinking? Systems thinking is an approach where we're taking a holistic look at these components, not one piece at a time, not silo by silo by silo, but we're trying to focus on all the parts and how they relate and how they interact over time within the context of larger systems. And a good example of systems thinking for knowledge graphs is this idea of what we call the AI flywheel, one of our archetype patterns. So what is the AI flywheel? It's as we have data in our graph, we can use that data to build machine learning models. Those machine learning models might do things like make predictions. What products might a customer want? How do we gather the feedback about what predictions people like? What do we take that feedback and then we add it to our data set and we get more data? Initially, our predictions may not be very good, but as we add more feedback, we get more data, we get better machine models, we make better predictions, and we get a positive feedback cycle. And that's why we have the plus in a lot of the center of our causal loop diagrams. So the AI flywheel is an example of an archetype of systems thinking in knowledge graphs. Another example of an archetype is what we call the tragedy of the commons, a story about how farmers in old medieval villages often had their own pastures, and there was a common area, and they had a rotation system so that each farmer could use it. But if the farmers overgrazed those common areas, they would become barren and nobody could use that. So whenever there's a common resource, we think of how do we share that resource so it's not abused. If there's too many people hitting the knowledge graph at the same time and performance is slow, people may not be using that. So how do we deal with shared resources where everybody needs to use those things? Another example, an archetype I call, is the Metcalfe law, or the network effect. And this is the value of standards in our knowledge graphs. Standards are so important. If we have a fax machine and nobody else, none of our partners have a fax machine, what's the value of the fax? Very little, because we can't send information to our suppliers or our customers. But if we have a standard way of representing data to move things in and out of the data that everybody understands, and we manage quality, then that network effect becomes a positive reinforcing thing. So standards are really important, and one of the archetypes that we use in we're deciding what data we should be put into our knowledge graph and how to standardize or normalize or canonicalize that data for consistency so that everybody can share the queries over this data. So I've mentioned now 3 archetypes, and I just wanted to mention that systems thinking often involves looking for those patterns across different domains. And this was all inspired by a book by Christopher Alexander called A Timeless Way of Building, which he used building architectural patterns. That prompted a group of people to create the Design Patterns book, what was often called the Gang of 4 book, and that looked at object-oriented design patterns. Now we're at the stage where we need to start to collect these enterprise knowledge graph systems thinking patterns, these archetypes, and put them together into a place where we can use them as a core training curricula so that we can train all of our architects to understand how to use these systems thinking patterns to help expand and grow our usage of these knowledge graphs. I just not going to go into too much more about systems thinking, but just to mention that there are many, many books on systems thinking. A lot of them are very good and insightful, but I don't want you to be intimidated by the number of books out there. Systems thinking is actually a relatively small number, about a dozen core concepts, like these causal loop diagrams, like feedback, like understanding positive and negative reinforcement. And I think most people can learn systems thinking in a few days. And the trick is, how do we apply this and find archetypes that are appropriate for our internal knowledge graphs, and when to apply those, and how do we use that to find out how to apply those resources most effectively. One of the other things about system thinking I want to mention here is that software and knowledge graphs don't stand alone today. It is also tightly coupled with the hardware that we run it on and the variability of that hardware for different use cases. If you are familiar with TigerGraph's architecture, you may know that it is at its core an MPP system, a massive parallel processing, so that TigerGraph is designed from scratch so that you can have a distributed cluster of nodes, and they can all be working on tasks together and send their results back. TigerGraph is much more similar to Hadoop's MapReduce than some of the single node graph systems that often get tied up by having to sequentially do these tasks because they don't have enough distributed resources. So our goal is to figure out what is happening at serial, and can we make that parallel, and can we match that parallel processing to the appropriate hardware? One of the most important things that comes from the machine learning aspect is the rise of graph embeddings. Now, graph embeddings, I'm not going to go into the details, but it's basically a mathematical structure. It's a series of about 200 scalar vectors that we can associate with any vertex in our graph. And these numbers help us quickly find similar items in our graph. And we don't have to physically materialize this as a link, but we can use that at any time to calculate and find similar items. That means that once we have these vectors set up, and I used a picture here of about 200 scalar numbers, we can use those numbers to compare things and to do math on our vertices, to find similar things, to find subsets, to find cohorts, to do averages and subtract, and do all sorts of things that we never thought were possible using deterministic rules. These are statistics, and they don't really correspond exactly to semantics, right? There's not one vector that is just about gender or age of our members. They're all kind of merged together, but they're still very useful at finding similar things very quickly. Why is this important? And this is important whenever we're thinking about building recommendation engines. And my example here is a recommendation from maybe a bookstore like Amazon, where you have an item such as a book on systems thinking. And what you want to do is in the real time, find out how is this similar to other systems. And remember, you may have 10 million other items in your database. So comparing one item with 10 million items often takes a lot of time. This is really important because it's not just about product taxonomies and how things are similar in your product catalog. This is about finding similar customers, because recommendation is about finding that match between customer similarity, finding similar customers, what they like, what past had good outcomes for them, and your products. And all of these things can now have embeddings, because our data scientists have gotten really good at coming up with algorithms to help calculate these embeddings quickly. I should also mention that having regular CPUs calculate these similarity things often is very, very computational intensive. But the good news is we can do these things in parallel, and we can get sub 10 millisecond response rates for similarity if we think about our systems at the chip level too. So if you're familiar with how CPUs are different from GPUs, you know that CPUs are very, very good at taking instructions and running them one at a time, potentially 1,500 instructions in the x86 instruction set. GPUs, on the other hand, have a single instruction for multiple data called the SIMD instruction set. But they often aren't optimized for doing these similarity calculations. Luckily, we can go to a different architecture for like an FPGA, where we can rewire potentially 50 billion transistors in about 2 seconds. And we can reconfigure all of these transistors to do things like cosine similarity very quickly. And by understanding these graph algorithms and what makes them unique and how to use the right hardware, we can get both the flexibility and the performance and low cost of using flexible hardware also. I also just want to mention here that hardware is not just about graph, it's also about NLP. And a lot of these new vendors coming out are getting a huge amount of funding, $1.3 billion of new funding for AI hardware in 2021. NVIDIA is, of course, the champion, where they own a huge percentage of market space because they were very early. But now we see three challengers coming in: GraphCore, SambaNova, and Cerebus. And all of them are really taking a close look at how we get away from this SIMD architecture. And every one of these systems have massive numbers of cores that can all be doing graph queries independently and help us find insights into systems quickly. And just one example, we just ran some benchmarks. We built a BERT model for all of English language Wikipedia, over 6 million pages, 7.2 billion tokens. And we built that model in about 12 hours using a GraphCore hardware. So something that was used to be weeks to build these models, now we can start to do it in hours. So what does this mean for our strategy? Now let's take a step back and look about what are we trying to do here? And the key here is that when we think of systems thinking, we want to think of what we understand well, and we call that the data that we've modeled correctly. It's in our graph. We understand it. We understand the nouns, the vertices, the relationships, the edges, and their properties. But now we ask the question of all the possible things that we could add to our knowledge graph. Which ones could provide the most value? Where do we start our next project? And we call that edge between what we've modeled and we haven't modeled, the edge of chaos. Chaos is the things that we don't really know about the model. And most importantly, we don't know the value of modeling those things. In the past, many of our projects were done in isolation, little silos of projects, and every project was different and they had their own staff. And we didn't really think these projects were all related. Systems thinking asks us to take another step back and look at all the projects in our portfolio and ask the hard question: when is order relevant to our projects? When can we put a project in place that would make all these other projects go faster? Projects have vastly different sizes, and also they have impact on other projects. So we want you to start to use systems thinking to not think about projects in isolation. We want you to think of building infrastructure projects that will accelerate all your other enterprise knowledge graph projects. So to wrap it up here, I want everybody to start to think about how we define our enterprise knowledge graphs, not in terms of little vertical silos of things, but how we can look at this in a holistic perspective. I think these pictures of taking the flowers apart and arranging them based on their flower parts, what we typically would do in a relational database to put everything in rows of a table that are similar, is a good example of how difficult it is to assemble beauty. And I think, to me, when I'm starting to see a lot of the projects mature, I'm starting to see beautiful flowers come out of this. And what it means is that we're providing more value to our customers. We're providing deep insights about where we provide value. We're finding faster paths to that insight. And we're able to build a library of stories and our archetypes that help us define what our next projects will be. So just in closing, I want to thank three of the people that I have been working with over the years. Arun Bachu from Gartner, the best systems thinker I've ever met. Nikhil Deshpande from Intel, who's leading the Intel Puma project. I think we're going to see awesome things out of Intel in the very near future. And then Kumar Deepak from Xilinx, who is one of the people that led a lot of our FPGA TigerGraph enhancements too. So thanks you guys very much, and I appreciate working in your systems, and you've taught me so much about how we can apply this to add value to our customers. So with that, I want to just thank everybody for taking time. Please go, feel free to go to my Medium blog, connect with me on LinkedIn under Dan McCurry, and I'm looking forward to seeing everybody at the conference. Thanks. Bye-bye.